Now we have noticed that this psi-MO can be obtained by the linear combination of 1s orbital of A and 1s orbital of B. This phi 1s is the 1s orbital of hydrogen atom, and this suffix A represents the 1s orbital of hydrogen atom A, and this is hydrogen atom B. Now this C1, C2 represent the coefficient, that means C1 represent the amount of phi 1s A contributed to the formation of this psi-MO, and C2 represent the contribution of phi 1s B for the formation of psi-MO. That is the coefficient which represent the respective contribution of the orbitals. Now if I take this C1 and C2 square, then this square term represent the probability of finding electron in the phi 1s A and phi 1s B orbital respectively. Now we have noticed that both the hydrogen nuclei, HA nuclei of HA and HB, have the similar charge, +1 +1, and they are sharing a single electron, same electron. So the probability of sharing this electron is 50-50, same. So the contribution of this HA, that is the 1s orbital of hydrogen 1 A and the 1s orbital of hydrogen atom B, will be same, because they are occupying the electron in similar way, same chance. So this coefficient C1 and C2 will be same for HA and HB, and then we can write that C1 equal to C2 equal to C. Okay, now this equation 1 will be turn out to be this, plus C phi 1s A plus phi 1s B. Now the MO can be formed by another way, because we can take a additive combination or a subtractive combination of two orbitals. So there I am putting this plus minus sign. Now if I want to know the energy of the system, because we are not interested to interested to get the psi-MO, even we do not know the psi-MO, we can find out the energy of the system. So first we have to know what will be the value of C, because C is here we are considering as a constant, and which implies the contribution of these two atomic orbital for the formation of molecular orbital. Now this C is nothing, it is a normalization constant. So we can find out the value of C using the concept of normalization of psi-MO. This is the way to normalize the molecular orbital function. You must know this. You have noticed many times this type of normalization constant, normalization procedure. And this one thing I have to mention here, that this psi-MO square represent the electron density, probability of electron density in the molecular orbital, and when you have integrated over space with d tau, you will get the electron density, that is probability of finding electron in the molecular orbital. Okay, that is one thing. If you can ignore this thing, you just remember this thing, that is integration psi-MO square d tau will be 1. Now in place of psi-MO you put the plus combination, additive combination, then we have this type of relationship which will be equal to 1. Now if I separate this, I will have three integral. First integral involve phi 1s A, phi 1s A d tau. Second is phi 1s B, phi 1s B d tau, and here will be d tau. Now this integral and that integral similar to the normalization for 1s A, phi 1s A. So that will be give out to be 1 and 1. Now the third term will be 2 into integral phi 1s A, phi 1s A into phi 1s B d tau, that will be 1. Now we have previously noticed that this type of orbital may be orthogonal, but in present case this orbital will not be orthogonal, because if I go to this this representation that Ha is the first nuclei, this is second nuclei and electron. The position vector are Ra, Rb, that is Rb and R1. So the difference, and this is the difference is Rab and this is Ra and this is Rb, small rb. With electron, these are denoted as small ra, small rb and capital Rab. That is the crystals. So if I look at this, then a electron is centered in the two nuclei. That is the orbital for electron. This single electron will phi 1s a and phi 1s b. Now this phi 1s a and phi 1s b are centered at the what at the nuclei A and B nuclei. That is nuclei A and B, nuclei of HA and HB. Okay, HA and HB respectively, like this way. Now when they have a common zone of sharing, okay, they are sharing in a common zone. So they are in these two places, when they are sharing this common zone, at this place I can have electron density. That is, at the sharing place, there it is not that there is no electron present. So there will be some electron when they are forming this type of overlap, and this overlap is nothing, this integral phi 1s a and phi 1s b. And this type of integral is nothing, that is contain two nucleus center and one electron. Two center is sharing one individual electron, one common electron. So this type of integral will not be vanished, and they are, in this case, they are will not be orthogonal. They will have some value. They will have some value, and this integral is known as overlap integral. And this overlap integral is a two-centered one electron integral, and it is denoted as SAB. That is a overlap between A and B, atomic orbital of A and B. So if I consider for pure case, that is first integral and second integral in the expression, then it will be SAA and SBB, and both SAA and SBB will be 1. So this integral is the overlap integral for A and B. Now I can write this c square into, now can I write this c square into 1 plus 1 plus 2s1. I can turn out to be this type of relationship. Then if I this type of relationship, again one can say, how can I calculate this overlap integral? This overlap, the value of this overlap integral is can be calculated using a special type of coordinate system, and this special type of coordinate system is elliptic coordinate. Okay, we are not bothered about this to find out the overlap integral. Without this, we can find out many type of interesting parameter of the system. Now we can write this as a c square plus 2 in c square into 2 plus sa equal to 1. So I can have a c value like this. Now we are considering only plus combination. This is for plus combination. So we are denoting this coefficient c as plus, superscript plus. Then for minus combination, I can have this type of relation, minus SAB, and this will be superscript minus. That is the coefficient are symbolized in different sign in their superscript. Okay. Now how can I determine the energy of the system? that is energy of the molecular orbital. So the way to find out the average energy of the molecular orbital to integrate using a Hamiltonian operator. Now we can construct that Hamiltonian by considering the Born-Oppenheimer approximation. We'll do this in the next class.